This is part 3 of the lecture on statistical inference for linear regression. We will go through a numerical example of the statistical test for regression coefficient, linear regression of systolic blood pressure on gender, age, and education, was done. Let's look at results related to x3, which is the binary variable for high school graduates. B3, the estimated regression coefficient for x3, was -1.28882, and S3, the estimated standard error for B3, was 0.64192. So the test statistics, T3, which is the ratio of B3 to S3, is -1.28882 over 0.64192, which is approximately -2.01. The null hypothesis is that, beta 3, the true value of regression coefficient for x3, equals 0. It can be shown, using the t-distribution, that if beta 3 is 0, then the probability that T3 is greater than or equal to 2.01, or T3 is smaller than or equal to -2.01, is 0.0447. We can also say, the probability that the absolute value of T3 is greater than or equal to 2.01, is 0.0447. This 0.0447 is the p-value of B3 by the two-sided test. This graph shows how the p-value was obtained. This is a graph of t-distribution, with a degree of freedom of 4025. Based on some mathematical assumptions, it can be shown that, if the null hypothesis is true, that is, if beta 3 is 0, then the test statistics, T3, asymptotically follows this t-distribution. Not all t-distributions are identical. This is the t-distribution with a degree of freedom of 4025. The degree of freedom was determined as the number of cases, 4030, minus the number of independent variables, which is 4, minus 1. The t-distribution with a high degree of freedom is almost identical to the normal distribution. The horizontal axis indicates values of t, and the area under the curve over a certain range on the horizontal axis represents the probability that t falls in the range. The area under the entire curve is 1. The computed value of T3, minus 2.01, is indicated on the horizontal axis. The red area on the left of minus 2.01 is 2.235% of the entire area under the curve, which means that if the null hypothesis is true, the probability that T3 is less than or equal to minus 2.01 is 2.235%. There is another red area, which is on the right of plus 2.01. Since the t-distribution curve is symmetric around 0, the red area on the right side shows that, if the null hypothesis is true, the probability that T3 is greater than or equal to 2.01 is 2.235% as well. Combining the two red areas together, this graph shows that, if beta 3 is 0, the probability that the absolute value of T3 is greater than or equal to 2.01 is 4.47% or 0.0447. This is the p-value by the two-sided test, and the p-value by the one-sided test is shown by the red area on the right side, which is 0.02235. In this section, we mainly follow the standard procedure of two-sided test of regression coefficients for linear regression, because the two-sided test is more widely used than the one-sided test. The mechanics of the one-sided test is essentially the same, and the p-value by the one-sided test is always a half of the p-value by the corresponding two-sided test, due to the symmetry around 0 of the t-distribution. This slide shows a part of computer output of the regression analysis. This is not a SAS output, but formats of output of regression analysis are similar among various statistical programs. Let's look at the row marked as HS, indicating those who have graduated from high school, but not from college. It is shown in the row that B, the estimated value of regression coefficient for the binary variable, HS, is -1.28882, and S, the estimated standard error of B, is 0.64192. It is shown in the next column that T, the ratio of B to S, is -2.01, and in the rightmost column, the p-value, the probability for the absolute value of T to be greater than 2.01, is shown to be 0.0447. The p-value is smaller than 0.05, i.e., the value of B is statistically significantly different from 0 at the 0.05 level. The test statistic T follows the t-distribution with a degree of freedom of n-k-1, where n is the number of cases and k is the number of independent variables. This makes it possible to compute not only the p-value, but also confidence intervals for beta, that is, confidence intervals for the true value of the regression coefficient. In order to compute a confidence interval, we need to specify a level of probability for the confidence interval, such as 99% confidence interval, 95% confidence interval, and 90% confidence interval. Let Q be a value, in percent, of probability. So a Q% confidence interval for beta means that the probability for beta to be in the interval is Q%. Now let's follow, as an example, the computation of the 95% confidence interval for beta for high school graduates. 6. We start with the general formula for T, i.e., T is the difference between B and beta, divided by S. This T asymptotically follows the T distribution with a given degree of freedom, which is 4025 in this case. This is a graph of the T distribution. The horizontal axis represents values of T, and the vertical axis is related to their probabilities. Two values of T, plus 1.961 and minus 1.961, are indicated on the horizontal axis. The red area on the right of plus 1.961 is 2.5% of the entire area under the curve. So is the red area on the left of minus 1.961. This means the probability that T is greater than or equal to plus 1.961 is 2.5%, and so is the probability that T is smaller than or equal to minus 1.961. Therefore, the probability that T is between minus 1.961 and plus 1.961 is 95%. Suppose T, or lowercase t, is a quantity, the probability distribution of which follows the T distribution with a degree of freedom of 4025. Then the probability that the lowercase t falls between minus 1.961 and plus 1.961 is 95%, or 0.95. It can also be shown that the uppercase T, which is a test statistic obtained from the results of the regression analysis, asymptotically follows the T distribution. Then, the probability that the large T falls between minus 1.961 and plus 1.961 is about 95%. By replacing the uppercase T by B minus beta over S, and rearranging the terms, we get that the probability for beta to fall between B minus 1.961 times S and B plus 1.961 times S is about 95%, too. So these two quantities, B minus 1.961 times S and B plus 1.961 times S, are the lower and higher ends of a 95% confidence interval for beta. In the example of beta coefficient for high school graduates, B3 was minus 1.289, and S3 was 0.642. Substituting these numbers into the equation, we get the range between minus 2.547 and minus 0.030 as the 95% confidence interval for beta 3. By the way, although we can get many 95% confidence intervals for beta 3, this is the only 95% interval that is centered at B, which is minus 1.289. We usually get the 95% confidence interval for beta, that is centered at B. So, now we understand that computation of the test statistic T from results of regression analysis, and placing the value of T in the T distribution, produce both a p-value for B and confidence intervals for beta. Now, let's return to p-values. It is important to be aware of the distinction between statistical significance and substantive significance. When the sample size is very large, a statistically significant result may not necessarily be substantively significant. Even when the regression coefficient is very close to zero, a large sample size may make it statistically significant. It means the true value of beta is unlikely to be exactly zero, but it is likely to be very close to zero. For example, suppose the estimated value of regression coefficient of an independent variable, x1, is 0.02. This could be substantively significant or insignificant, depending on the scales of x1 and y, their variations, and substantive characteristics of those variables. Suppose that in the substantive context, any absolute value of the coefficient below 0.1 means that the relation between x1 and y, controlling for the other x's, is negligibly weak. Nevertheless, if the sample size is large, then the 95% confidence interval may be very small, like between 0.01 and 0.03, and the p-value may be smaller than the widely used cutoff point of 0.05. This means that beta is unlikely to be exactly zero, but the relation between x1 and y is negligible in the substantive context. Special caution is needed about regression results for categorical independent variables. If a binary variable for a category of a polytomous variable is used in the regression analysis, the p-value given to the coefficient for the binary variable determines statistical significance of the difference between the category and the reference category. So, if the reference category is changed, the p-value for the binary variable will change, too. Also, in case of a polytomous variable, the computer output of the regression analysis should show the p-value for the difference between each category and the reference category, but not the p-value for the difference between two categories that are not the reference category. In such a case, the easiest way to get the p-value for the difference is to do another regression analysis with a different reference category. Let's look at another example. A regression analysis of systolic blood pressure was done, with data on women only. The independent variables are age and education has three categories. Suppose that first, a regression analysis was done using graduated from college as the reference category of education, and regression coefficients were obtained for the other two education categories, 8.736 for those who have not graduated from high school, and 3.976 for those who have graduated from high school. The p-value for the 8.736 point difference between those who have not graduated from high school and those who have graduated from college, controlling for age, was 0.000, and the p-value for the 3.976 point difference between high school graduates and college graduates was 0.051. But the p-value for the difference between those who have not graduated from high school and those who have graduated from high school was not obtained, so the statistical significance of the difference was unknown. So, the second regression analysis was done, using graduated from high school as the reference category. Now the regression coefficient for those who have not graduated from high school has changed from 8.736 in the first analysis to 4.760 in the second analysis, and its p-value from the second analysis, which was 0.009, is about the difference between those who have not graduated from high school and those who have graduated from high school. This diagram summarizes the process of computation of the p-value. From results of the regression analysis of the data, and the null hypothesis about the regression coefficient for xj, the test statistic t, or uppercase T, is obtained. On the other hand, based on some mathematical assumptions, the test statistic t, or the uppercase T, is considered to asymptotically follow the t distribution, or the lowercase t distribution, with a degree of freedom, which is determined by the number of cases and the number of independent variables. By placing the test statistic t in the t distribution, we can compute the p-value, which is, in the case of two-sided test, the probability that the absolute value of test statistic t is greater than the absolute value of the obtained t, if the null hypothesis holds true. A confidence interval for beta j can be obtained in a similar way, by setting beta j as unknown, instead of 0.